In today's lesson, we're going to be talking about the quotient rule. For the quotient rule, we're assuming we have functions f and g, and we're assuming that these functions are differentiable. If I want to go ahead and calculate the derivative of f divided by g, it turns out that the derivative of f at x divided by g at x is equal to the bottom, in this case g at x, times the derivative of the top, which is f prime at x, minus the top, times the derivative of the bottom, divided by the bottom. Alternatively, you can also express it without the x's and just write it as bottom times derivative of top minus the top times the derivative of the bottom over your bottom squared. So let's take a look at a proof of the quotient rule. So to start us off here, we'll let f and g be differentiable functions. I'm going to define h at x to equal f at x divided by g at x. If that's the case, what I'm going to do is I'm going to isolate for f at x here, in which case we get f at x is going to be h at x times g at x. I'm going to go ahead and apply the product rule to this expression, taking the derivative of f prime at x. When I do that, you've got your first times derivative of your second plus your second times the derivative of the first. Now I'm going to try to isolate for h prime at x. And the reason for that is obviously I'm looking to find the derivative of h at x, as that's the quotient of f at x and g at x. So I'm going to go ahead and isolate for h prime at x here, in which case we get g at x, h prime at x is going to equal f prime at x minus h at x, g prime at x. Divide across by g at x here, we get f prime at x minus h at x, g prime at x, all over g at x. Recall that h at x was defined to be f at x over g at x, so I'm going to go ahead and substitute that in to my expression here. I'm going to replace this h at x with f at x over g at x, in which case we get h prime at x is going to equal f prime at x minus division of f at x over g at x times g prime at x, all divided by g at x. The next thing I'm going to do here is I'm going to go ahead and get a common denominator in the top. So to get a common denominator in the top, I'm going to multiply f prime at x by g at x over g at x. Doing that, we get f prime at x times g at x minus f at x times g prime at x over g at x. This whole thing here represents a common denominator in the numerator. We still have our g at x left over from the denominator. Now you'll notice here we essentially have fraction divided by fraction. And when you have fraction divided by fraction, we're going to go ahead and multiply by the flip of this denominator, in which case this becomes bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And we have proven the quotient rule. Let's take a look at some examples. So for our first question here, we want to find y prime. In this case, root of x would be our f at x, and x squared plus 1 would be our g at x. So y prime is going to be the bottom times the derivative of the top minus the top expression times the derivative of the bottom all over the bottom squared. Sometimes it's easier to express things as their root in terms of cleaning things up and simplifying. So I'm going to go ahead and do that. When I do that here, I can see that to get a common denominator in the top, I only have to multiply the top and bottom by 2 root x. Doing that, I end up getting y prime is x squared plus 1. Now this expression here, you end up getting 2 times 2 is 4, and x times root x here, x times root x becomes x squared. In that entire expression, we got that common denominator, so that'll be over 2 root x, and then we divide the entire thing by x squared plus 1 quantity squared. And again, we're dividing fraction by fraction. So simplifying, this becomes minus 3x squared plus 1 over 2 root x times x squared plus 1 quantity squared. And this would be the derivative using the quotient rule. Let's try another. For the next question here, we want to find g prime at t. Again, using the quotient rule, we're going to go ahead and take the bottom times the derivative of the top, which is 4t plus 3, minus the top, times the derivative of the bottom is just 1, and we take that entire expression and divide it by the bottom squared. Now going ahead and distributing here and expanding and simplifying, we get 4t squared plus 3t minus 4t minus 3 minus 2t squared minus 3t minus 1, and divide the whole expression by t minus 1 squared. Collecting like terms here, we get 2t squared minus 4t minus 4, all divided by t minus 1 squared. Factoring out a 2, we get 2 times t squared minus 2t minus 2, all divided by t minus 1 quantity squared. And now we have here the derivative of this function using the quotient rule. Let's take a look at another example. For this example here, we want to find the equation of the tangent line to this curve here at the point 1, negative 4. So to find the equation of a tangent line, we need a slope and a y-intercept. Well, my slope is just my derivative evaluated when x is 1. So let's go ahead and do that. So we're going to take our derivative here. So this will be dy dx is the bottom times the derivative of the top is 3 minus the top times the derivative of the bottom is negative 3, all divided by the bottom squared. Now we don't have to simplify this expression here because I'm interested in finding the value of the slope of the tangent equation, in which case I can just take my derivative and evaluate it when x is 1. Doing so, we get, this will be 2 minus 3. It's going to be negative 1 times 3 minus, this expression here will be 1 plus 3, so that'll be 4 times negative 3, and the bottom will be negative 1 quantity squared, in which case we get negative 3 plus 12 over 1 is 9. So therefore, the slope of this line is 9. I want to find the y-intercept. So my equation is y equals 9x plus my y-intercept. Subbing my point in, we have negative 4 equals 9 times 1 plus my y-intercept, and my y-intercept is negative 13. Putting this together, the tangent equation is y equals 9x minus 13. All right, let's try another. So for this equation here, they want you to find the equation of the tangent line to the curve y equals x minus 1 over x plus 1 that are parallel to this line here. So if the slope of the tangent line on our curve here were to be parallel to this linear equation, the straight line here, we would have to have the same slope. Well, the slope of this line is going to be, or any line in standard form, is negative a over b. In this case here, my a value is 1 and my b value is negative 2. So the slope of this line is a half. So I want to find all tangent equations on this curve that have a slope of a half. Well, therefore, I first have to calculate my dy dx. So dy dx is going to be my bottom times derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Now in this situation here, I want to set my dy dx equal to a half, and I'm going to simplify the top, in which case here we get x plus 1 minus x plus 1 all over x plus 1 quantity squared. Continuing, we have 1/2 equals 2 over x plus 1 quantity squared Multiplying across, x plus 1 squared is 4. X plus 1 is plus or minus 2. X is negative 1 plus or minus 2. So we take on two values here, negative 3 and 1. So there's two x values whose tangent equations have slopes of a half on this curve. Let's go ahead and find each tangent equation. So to find each tangent equation, I have to find a point here. So I have a point x equals minus 3. The corresponding y value would be evaluating x at minus 3 here, in which case we get negative 3 minus 1 over negative 3 plus 1 is equal to negative 4 over negative 2 is going to be 2. So the point that the tangent equation touches is negative 3 and 2. Therefore, the equation is y equals 1/2 x plus my b value. Subbing my point in here, I get 2 equals 1/2 times negative 3 plus b. And we get b equals 2 plus 3/2 is going to be 7/2. So the tangent equation is y equals 1/2 x plus 7/2. Finding my second tangent equation, we're going to evaluate x when x is 1. So my y value here will be 1 minus 1 over 1 plus 1, which is 0. So therefore, the point that the tangent line touches on the curve, x minus 1 over x plus 1, is going to be 1, 0. So therefore, my equation is y is 1/2 x plus b. Subbing my point in here and solving for b, I get b is minus 1/2. So the second tangent equation is y equals 1/2 x minus 1/2. So these are the two equations that have slopes of a half on the curve x minus 1 over x plus 1. All right, that concludes our lesson for the quotient rule. Thank you.